Oh, geez. That's how good they were. I don't know. What do you think about that metal nails through concrete? Fairly excited. Was it the Structural Engineering Podcast?
Hey, welcome to this week's episode of the Structural Engineering Podcast. My name is Max.
And I'm Zach.
This week, we have a good one for you. We sat down with the guys at Structural Engineering Basics. They told us everything they know about high-rises.
This one's pretty cool. It's Mustafa and Noah are very, very knowledgeable. And a little sneak peek towards the end of the episode, Mustafa talks about working in Dubai. I think you guys are going to really like this one, and we're excited for you to listen.
Oh, and before we get to it, they've got a course for contractors, architects, and new engineers, an intro to structural engineering, which I think is a really cool thing. We got to take a little peek at it, and they have a discount code for 25% off SEP listeners. I wrote it down somewhere. That is SEP25 off. All capital letters, SEP25OFF. So check them out. Their website is down in the show notes, and it is structuralengineeringbasics.com.
Hey, everyone. Thanks for having me on the show. I'm Noah Moskovich, and I am a structural engineer in Winnipeg, Manitoba, Canada. So I've been a structural engineer, or I graduated around 8 years ago, and I got lucky enough to get a job at one of the city's top structural engineering consulting firms. Now I'm at the point where I'm project managing and designing the projects at the same time.
My name is Mustafa Almogi. I'm a structural engineer. I worked in engineering consulting in Canada with Noah for many years. I'm originally from Egypt, did my undergrad and master's degree in Cairo, Egypt. And before moving to Canada to do my PhD, I worked in Dubai for a while. And that got me really interested in tall buildings, the design of tall buildings and reinforced concrete structures. Looking back, that was a very interesting experience. It enabled me eventually to go back into consulting and doing tall buildings and reinforced concrete and design, and also teaching. And that worked out to get an opportunity, a chance to do both, to be working in consulting and getting experience, and teaching as well. And that always got positive feedback from my students when I share with them real life projects and things like that. So this is awesome. Thanks for having us.
Our pleasure. I always appreciate when teachers had some real world experience to share. I mean, it's nice to be totally
Absolutely.
On the study side as well, but it's cool to have some stories to back it up, I always think.
Absolutely.
So you guys, you worked together originally in Manitoba, but we're going to talk about tall buildings eventually here. But first, I want to talk about Structural Engineering Basics, which is kind of a coursework and program that you guys put together. Can you tell us a little bit about it?
Sure. So we decided to put together this platform about a year and a half ago that teaches non-structural engineers the basics of structural engineering. So us as structural engineers, we have a pretty good understanding. Obviously, that's what we do. But there's plenty of people we work with and maybe people who want to be structural engineers in the future that we thought if only they had a better idea of how we construct buildings or how we design buildings, it would make their lives easier. It'd give them a better understanding of their overall picture. So if there's an architect who is working with structural engineers daily, or contractors who are always communicating from site to the structural engineer in the office, or owners who are investing millions and millions of dollars in big structures, we thought we should give them a platform to give them a bit more knowledge on how structures are designed. Let's say what types of loads we use to design, like why are we supposedly so conservative in our design. So we did, before we started this whole platform, and we have a website with blogs, YouTube videos, we have free guides, we've got a lot of free content on there. We did market research and we asked these target audiences, what type of content do you want to see? And ultimately, our goal was to make a course, an online course, like something that they can learn all this information in one spot. Because we looked out there and we did some Googling, and there really wasn't much out there when it came to teaching someone about structural engineering in a simple way that's not super time consuming. It's a longer course, but they can watch it on their own time. It's pre-recorded, and they can do it on their own schedule, and they can ask us questions as they go, because we know all our target audience live busy lives. Architects, for sure, they're on the same tight deadlines as us. Contractors, we found most of our students so far in the course have been contractors, a few architects here and there, and we've actually had surprisingly a decent amount of civil engineering new grads who want to become structural engineers. It's a lot of real world stuff we talk about in the course, and eventually we think we will branch off and do different ones. We actually just came up with a new course just for students, but it's not about anything technical, and it's for all engineering students. And it is to help them prepare for life after graduation. Not many students actually know what it takes to get a job once they graduate. So we teach them, half of the course is going to steps, what it takes outside of the technical steps. So like networking tips, job interview tips, resume tips. And then the second part of the course is once you get that job, once you finally get that dream job, like what's the day in the life of an engineer like outside of crunching numbers?
Yeah,
right.
Yeah.
There's so much that I never knew when I first got my job. It took me years to learn, but we love to get those students and those new grads head start, and so they know what they're doing when they get in.
I really like what you guys are doing, and we talked about this the other day when we did that Instagram live stream. That one thing I found helpful, and I've definitely directed some people towards, is your guys' blog. I think you've done a really good job to put content on there that's easily to be understood by anybody, and kind of goes over some basic limits and items within structural engineering. So if you guys listening, if you want to learn more about them, they have an awesome website, an awesome blog.
Yeah, okay. Well, our website is structuralengineeringbasics.com. You can find us on Structural Engineering Basics on Facebook and Instagram too. But for your listeners, we thought since you're all really into structural engineering, and if some of you are students or new grads, and you want to know what it's like, what structural engineers do when they design structures, what you're going to be doing, you can sign up for either one of our courses. So we have the student course. It's a bit cheaper and it's more geared towards a student's budget. And we also have the bigger full course that we've had students take it, and they definitely recommend it. So we're going to give you, the listeners, a discount code. So if you do, it's for Structural Engineering Podcast. So discount code will be for 25% off either of our courses. And the discount code will be SEP25 off. So all in capitals, SEP25 off.
Perfect. Yeah, we'll throw in the show notes down there. And I guess with that, let's get into high-rise construction.
Ooh, yeah. So this week's topic is on high-rise construction. We talked with Noah and Mustafa. It's probably about 3 or 4 months now, and we kind of got to know each other a little bit and started finding out that that's what they do. Both of them have experience in it. As Noah discussed, he has experience up in Canada doing some high-rise structures, and then Mustafa has some experience as well in Dubai and other countries around the world. So we thought, no better topic to me than high-rise construction. It's the coolest of the cool. That's, I don't want to talk for Max, but myself, really, like when I was in school, that was like the coolest thing. I was like, man, I'm getting out of school. I'm just going to go do skyscrapers all day long. Yeah. Turns out that's not how the world works.
I feel like when you're leaving school, it's either you want to go do giant bridges or giant buildings. And
yes,
almost everybody doesn't, because there's just, they're not constructed that often. Like a high-rise is relatively a pretty unique thing. So tell us a little bit about your individual experiences. Noah, you were saying some 14-story buildings, and like you said, this is all very relative, right? I'm right now working on a 10-story, and that'll be the highest thing in Salt Lake. I don't know if you'd call that a skyscraper by any means, a tall building. There's much taller buildings, but like for me, that is huge. So that's pretty cool. But what else have you guys worked on?
So I totally agree with you. Like there's something about tall buildings that it's so cool. And I feel I'm so grateful. I was lucky to get this opportunity to go and work in Dubai right after school, right after graduation. The company I was working with at the time were like very interesting tall buildings. They were like in the 60 floor range, like 60 floor buildings. And it was a very interesting experience because, so for me, that was like the first kind of tall high-rise building project. I have a lot to learn. And there is also like the pace of the work that was back in 2005. The time schedule was like very challenging. It was very challenging. It was like a lot of meetings, a lot of changes, and clients very demanding, strong competition. So it was a very interesting experience. So just getting a chance to understand the basic kind of concept and what you need to do for like a successful design, you learn on the job, on the go, like, you You take it kind of one step at a time. You start to realize a tall building is very similar to any regular building with just like significant lateral force, because the taller it gets, like the wind and seismic, now they need their own kind of prominent systems. And then you spend a lot of time satisfying these conditions. You don't want the building to move sideways too much when it's like windy, or you want it to stay standing in the case of an earthquake. And a whole sort of challenges come up when you start kind of thinking hard about the design of a tall building and what goes into it, and all sort of things, like, you know, from the foundations with the heavy loads, what are you going to do about that? Lateral loads, vibrations. They're very cool projects.
Yeah,
like it's cool to work on them.
I really want to ask, and you touched on this right before, this is not the engineering side, but I'm very curious about kind of the feel in an office that does these really high-end projects. Is it like more intense, do you think? Kind of like cutthroat?
It's a lot of responsibility, right? And then you want to do a good job, good work. You know what? I found them similar to other projects. They have their own like deadlines. Work needs to be done by a certain time, and then the pressure is on. Like, okay, now we have 40 floors, 60 floors, and you still need to meet your deadline. So it's similar in many ways to kind of regular projects, but there is also like that factor about like, yeah, that's going to be like one of the tallest buildings in like the city, or that's now a new record, like, oh, that's the tallest I've designed so far. So there is always that cool factor about it.
I no longer work with Mustafa. He's back in Egypt, so I'm still in Winnipeg. And I'll be honest, all of my tall building experience is working with him by my side. So Mustafa was a huge asset to our company when it came to tall buildings with his experience, and he was always the one doing the modeling. He would model it using ETABS, and he would do the modeling and he would give me the output. So I really don't know the complexity behind the tall buildings, other than I know that the wind loads are critical, and where we live, there isn't much earthquake loads to consider. But he would give me the loads, like the shears, the moments in the walls, axial loads in the columns, and we would work together and started to analyze the model, and I would use those loads to design the different elements. And I could tell you, back to your question about, is it sort of cutthroat when it comes to a high-rise building in the office and like bidding for it? But I don't remember the bidding process, but they're currently building the tallest building in Winnipeg right now, and Mustafa was part of that team at our office. So I remember, like, I sat next to Mustafa, we had cubicles right next to each other, and I remember how every day the pressure was on for that project. You always heard
secret project. No, realized you probably shouldn't have mentioned it, so he asked me to pull it out. All right.
It's a big new building. And they actually, this building, which is pretty cool, like, I think they built it 30, 40 years ago. It was only a 2-story building, but they designed the foundations and the columns and everything to place a high-rise on it. So finally, 40 years later, they decided, let's go, let's do this. We have the money, we have the investors, let's build this thing. But obviously a lot has changed, especially when it comes to foundation design. In Canada, I'm not sure about you guys, but we used to do allowable states or allowable design when it came to foundations. Now we do something called limit states design. So the capacities for foundations have been reduced. So maybe it was designed for 40 stories back then, or maybe it was 45, but we did whatever it took to get that structure like as light as possible, to pare down the loads so we can get that building as tall as we possibly could. So, and I remember like the RFIs, because that's a high-end project in our city. If Mustafa got an RFI, or if the partner in charge got something, she would come to Mustafa, like she would say, we need this answer yesterday, like do whatever it takes. So Mustafa had some late nights, and I'll let you talk a bit more about like figuring out how many stories we could do on that, and then just like how everything was tight.
Man, that's some really cool experience that both of you guys have. I'm definitely a little envious. So to start wrapping our heads around and starting all the way at the beginning, the project comes in-house to your engineering firm. What's the process like? You said you have a principal in charge. Would they start working through what the lateral and gravity systems are? Does the what's that like?
Or even before that, deciding how tall this can even be. Are you geotech way early and you're in schematics with everybody?
The example that Noah mentioned, that's kind of unique example. And this process has its own challenges because it was sitting on existing foundations and 2 existing floors. So you're absolutely right. The first question that needed to be answered that involved the structure engineering team was how tall can it be? Because it's sitting on existing walls. So that was a big phase. That was a big phase of the design because you need to consider everything. You consider, okay, what are the existing lateral resisting kind of core? Can you make it work with just these walls or just this core? And the answer ended up being no. You need more walls. So how much? What's the configuration? Do you need outriggers? And then there is the estimating the load part of it. So how much is the wind load on that thing? So you can use like the code, the standards as a guide, but then very quickly you realize that you eventually will need a wind tunnel test. You will need some wind tunnel analysis.
So just to jump out and just talk a little bit more on wind tunnel testing. This is something that probably most of you don't have experience with. It's fairly a rarity in our traditional buildings. So really where in the code is wind tunnel tested discussed, and that's ASC 716, chapter 31. It goes over all the wind tunnel procedures. I mean, you might ask, but why use a wind tunnel? Why is that applicable to something that you would do? And that's where we have to go back to chapter 27. The building must be regular in shape and defined as in section 26.2. We went over this in a previous podcast on wind design, so go check that out. But it says that if it doesn't meet those conditions, there's limitations where you can no longer use chapter 27. So in there it states that you shall then use the wind tunnel procedure specified in chapter 31. So if you have a building that doesn't conform to chapter 26 where it defines those limitations, then you'll have to start doing wind tunnel testing.
There is some discretion to be had here. Chapter 27 does have a method for determining force for a building of any height. Part 2 caps you out at 160 feet, and I think that's the number a lot of people use as this is the top of a tall building under normal circumstances. In the second condition, where you can go up to any height, the building code does have some restrictions, as Zach mentioned, and that's if you're seeing some weird responses from the building. And it's hard to predict that, especially us as structural engineers. We don't have quite the background that wind engineers do to anticipate this behavior. This would be vortex shedding, instability or galloping or flutter of the building. As the building gets taller, more slender, and the natural frequency increases, the likelihood of these conditions being created also increases. So at what height do you get a wind tunnel test? Well, that's up to your discretion, but 160 feet seems to be the point where you start to consider it.
And that also the process to get a more accurate wind load, like wind tunnel loads, you need to kind of zero in on the inertia, on the stiffness of your building. So you need to do a few iterations to get the walls in the right ballpark. And then you get the fundamental frequency for how stiff your structure is. And this information, the wind tunnel analysis kind of consultant, they need all that to start modeling your building and give you useful feedback. And then it goes in few cycles. So it's very interesting.
I want to ask about wind tunnel testing, because it's something that's never, I've never had to deal with or experience. You mentioned the coordination that's required in the beginning. How is the information given back to you? And is there any iteration in the project, say the building gets stiffer in design? Do you have to return that to them and say, what is the effect here?
Yes, that's a great question. And you're right. There was quite a bit of iteration. I would say 2 or 3 cycles. That was kind of the minimum. First, the wind tunnel consultant, they were very helpful. They walked us through the process. So they said, okay, we're first going to do what they call a desktop study. Before building a 3D model, before putting anything in any wind tunnel, they're like, okay, based on our experience, based on how tall your building is, based on this kind of part in the world where you're building it, we can give you some guidance, some guidelines, something to get you started. And then at this point as well, I shared with them my prelim kind of first version of the tower, the 3D model, the ETABS model. So they asked for very specific information. They wanted to know the first three modes of deformation, the fundamental frequency. So typically it's like the fundamental frequency in the X direction and in the Y direction and torsion. So they wanted to know how stiff the building is in these three directions and a layout of the tower in case there is like some wind turbulence or vortex because of the shape of the tower. They use all this information to do this desktop study or like to run a model basically and give us something to start with. And then that's the first kind of cycle. They give us back forces like loads per floor in X direction, Y direction, and they give us a torsion at each floor and load combinations. And I remember there were like a whole bunch of combinations because they were very specific about the how these loads work together. So they would be like I think like 100 load cases,
wow.
Something like that. Yeah. So in the X direction, mainly X, so positive and negative with different ratios with the Y and torsion. And then you do the same thing with Y and torsion, mainly Y with different ratios, mainly torsion with different ratios. And then I would take that in the 3D model and look for stresses in the walls and deformations. So can the walls with the thicknesses we're using now, can you fit enough reinforcing in them to resist the load? And there is also like the deformation. You don't want the interstory drift to be too big.
So what is interstory drift? The quick definition of interstory drift is the displacement of one story relative to the other. This is something that you should be looking at on multi-story structures and something that the seismic code and wind code very specifically state.
And another thing, it was very helpful, the study they did. They gave us some guidelines on the vibration. I know, Zach, we talked about how the vibration could make the occupants on the high levels kind of feel sick. So some acceleration can be felt and uncomfortable to humans. And that was very helpful to kind of guide us what is going to be within the allowable limit and if something needed to happen to the main lateral resisting system.
So to talk a little bit about building vibrations, what he's really talking about is horizontal vibrations due to lateral loading of wind or seismic. Vibrations are cyclic motions, and this is commonly discussed in structures as floor vibrations in wind and in seismic. And what you got to really think about is the stiffness of the building is changing how it's being loaded.
Wind loading tends to be more critical here because we're looking at a serviceability limit state. In fact, we'll use lower wind speeds such as a 10-year MRI to look at the acceleration at the top of the building and make sure the occupants are comfortable.
They're typically wind controlled from what we've seen, even in high seismic regions. Do you know at what height you kind of start seeing a move to wind control from seismic controlled at all?
That's a great question. So I think Noah mentioned like where we designed this project. Seismic was not the main governing force. So this building was mainly governed by wind. But that's a great question. I think the taller the building, the more kind of wind governed it becomes. Just because like how the natural frequency, how the fundamental frequency, the stiffness of the building with the base of the building shaking, that helps dissipate the seismic force. And it's just like the lateral load from wind that becomes the main governing factor.
Interesting. Yeah, that's something I've read in a couple of Structure magazine articles talking about tall building design, where even in high seismic regions, eventually you get to a point where the building is so flexible that, you know, the base shear reaction percentage gets pretty low and wind is actually a controlling factor there. But
yes.
So what height of a building do you change from a seismic controlled to a wind controlled? And specifically, we're talking in high seismic regions. Typically, the taller you get, the building becomes governed due to wind. And it goes back to a bit more of our building stiffnesses and how the load is being transferred through the building and the harmonics of the building. An example of this is the Rainier Square Tower in Seattle, Washington, which is a high seismic region. That building is actually governed by wind.
All right, so when you're looking at whether it's wind or seismic, you alluded to this a little bit, but what type of lateral analysis is done? And maybe in combination, what software do you use to do that analysis?
The main software I've used, and it's very interesting. I've used it in Dubai, in Canada, in Egypt. It seems to be a very successful software. ETABS. The thing with ETABS, it makes things much easier with the lateral load analysis, because it does all this dynamic properties of the structure. Some textbooks and some codes gives guidelines how to calculate the fundamental frequency of a structure, and basically what that is, it's a characteristic of the building, of the structure. When the stiffness of a building is within a certain number, if it's going to move naturally, it's going to take a certain time to finish the cycle, and you reverse that becomes the frequency. And that what that number defines is like the dynamic properties of the structure. And you need this number for different things. For tall buildings, the dynamic effect of wind load is more prominent. So just like a static approach of wind becomes less conservative. So the wind load becomes a function of the fundamental frequency of the building. So there is a bit of iteration there, because the load depends on the stiffness. So you start with something, and then you go kind of double check your load, or double check that your frequency is still within the range that you assumed. And then you size some walls, and you already need to assume some thickness to start building the model in the first place. So yeah, it takes few iterations before you can get things going.
So is this something closer to like a modal response spectrum analysis that we would be familiar with in seismic, how you're running this wind analysis?
So it's different. I don't think it's like the spectrum analysis for seismic. I think it's much simpler. It's still point loads, or like it's a pressure on the surface of the building. And ETABS can help calculate that. You just set the parameters, and it would assign point loads at the center of rigidity for each plate, for each floor. And the amount of force, that's the number that changes.
I see.
Because force per floor depends on the overall stiffness of the tower. That's kind of the response of the effective wind on the tall building. It depends on its own stiffness.
Okay.
As you get taller, there's a lot of guidelines about using outrigger systems. You've kind of already brought that up. Where do you see, at what height are you starting to use outrigger systems? Maybe go into a little bit of what that is and why you'd use one?
Yes. So a good way to kind of understand the outrigger system is your main lateral resisting system is, say, a concrete shaft in the center of the tower, in the center of the building. And then the rest of the floor area, it's mainly gravity, vertical load resisting elements like columns and things like that. So an outrigger system is going to introduce shear walls or solid walls that don't have to be necessarily continuous all the way to the foundations. This brings like a rigid floor. Like you can have it at like 1/3 and 2/3 of the building that starts to engage the perimeter columns or the perimeter system to improve and increase the stiffness of the structure. So it's something I would resort to when I can't meet the lateral deformation limit. You know, there is a ratio between like the height of each floor or the height of the tall building and the displacement, the lateral displacement. This ratio shouldn't exceed a certain limit. And it's very easy when you get to like 40-story buildings or like 60-story buildings, there's so much deformation at the top, and you need to control it. You need to limit it. The only way, or one of the most effective ways, is to increase the stiffness. So you can do that by adding more walls or adding outriggers, like just solid walls at key points in the tower. And also it helps to use stronger material. So you can play with higher compressive strength concrete, like views, like you can start using like the 50 MPa, 60 MPa.
That's 7,000 to 8,500 psi.
And you can go up, and that obviously improves the E as well, the modulus of elasticity.
Are you using 80 KSI or whatever SI? Are you using high strength rebar as well?
We use the normal ones, like the ones we use in MPa is like 400 MPa.
That's our typical 60 KSI bar.
That would be the normal strength, Noah, right?
Yeah, I know in the US the new code provisions are now allowing very, very high strength rebar. They've done a lot of testing. The big issue is the rebar being brittle, and I guess they found that with certain detailing you can get up pretty high to get away from all that congestion, and there's always issues of consolidation and items like that.
Yeah, we're using some 80 KSI in a project I'm doing right now to just lower the piece count on rebar, avoid some congestion. But yeah.
Mustafa, what type of are you pretty much just seeing concrete cores? That's your background? I know as you get really high, concrete's probably one of the only materials you're really getting to use.
That's my experience for most of the tall buildings I've worked on. The main system was reinforced concrete shear walls. But there are really cool systems out there. Like once you get to the super tall buildings, so along the way you will start to introduce like outriggers. So yeah, Zach, we talked about how this can improve the stiffness and help limit and control the deformations. And then if you think about it, if you want to increase the stiffness, you want to start engaging the perimeter columns and like introduce lateral resisting systems on the perimeter of the structure. So that way, the whole tower is like one big kind of tube or structure connected together with the central core. And this is when you can introduce exoskeleton, like exterior trusses, basically steel trusses that are helping to resist the lateral load.
Is there a system that gets you the most pumped to use?
I would love to get a challenge like using something like that, like introduce like a steel frame or truss on the perimeter that is visible. I always love structures that show their structure elements.
Oh yeah.
To me, that looks like so cool. I don't know if like that's the structure engineer in me or like they're aesthetically they look better, but that would be something really interesting to I think by the time you have the need to introduce systems like that introduce exterior skeletons, that would be a very tall building, like a super tall building. So that in itself is so exciting. Mm-hmm. And it comes with all set of challenges to build something that tall.
Yeah, I think it would be pretty cool to do a system that uses viscous damping or a mass-tuned damper. Probably never, yes. But
we also talked about this in the Instagram live, right? It's I couldn't believe the effect of like a mass that is tuned to help control the vibration of a structure until I saw it. Like it was like a small model, and you get like a simple cantilever to vibrate, and then you put a damper with a calculated mass and stiffness and springs to control the vibration of that, and it completely changed the behavior. It's fascinating, really cool stuff.
Oh, that's so neat.
So Noah, Mustafa sounds like he just goes out there and designs these massive skyscrapers all day, every day. You've got some experience with, smaller buildings as well as these big buildings. What are things that are surprising to you that are similar between a larger building and a smaller building, and what things are drastically different? I'm sure we can probably take a good guess at those, but what from your experience have you seen?
Well, other than looking at like wind and sway of a building and dealing with those vibrations, and the design process is, like you would probably agree, is the same. We have gravity load, vertical load on the column. So it really doesn't matter if the load is 1,000 pounds or 1,000,000 pounds. We're still using the same processes to design each of those elements. So whether the span for a tall building, if there's going to be a huge clear span, is 100 feet versus 20 feet, we're still using the same principles. When it comes to foundation, I guess, say the same type of thing. You're just seeing way bigger foundations and deeper foundations or different types of systems depending on the load. But yeah, like when you're looking at a shear wall, if I have a shear wall in a 3-story building, there's going to be moment and shear in that wall that I have to resolve the same way. So if it's a 40, 50-story building, yeah, the rebar is going to be more concentrated to the end and the uplift is going to be a lot more, but the way we get there is the same. So to me, that's how I picture things, because I don't have the expertise that Mustafa has in tall building design. So when someone hands me a 12-story building, as long as I have an expert like Mustafa there doing the modeling and giving me the loads, I think of it the exact same way as a 4-story building, a 2-story, 1-story building.
On the flip side of the earlier question, things that remain the same, are there anything that stand out as being really interesting that change when buildings get taller, like things you wouldn't have expected until you did your first design?
Yeah, I would say getting lateral loads into the ground. So you have these huge lateral loads in each direction. And when it gets to the lower floors, or when it gets to the ground, if there isn't something like a basement or 2 stories deep where you have these walls that the lateral load can sort of push on the walls and the earth pressure against the walls can resist those lateral loads, you have a problem that you got to deal with. How are you going to get those lateral loads into the ground? So that building that we did was a 12-story building that had no basement. So at the main floor, we typically would just have, if it's a 1-story building, let's say a 2-foot deep grade beam or a 3-foot deep grade beam. But we needed to find a way. It could either be battered piles, like were we going to use that? That came across, or that was a thought that we came up with. That's angled piles to get that lateral load transferred into the ground. But what we ended up doing was deepening the perimeter beams. So the beams that had soil built up against them, we figured out how deep they needed to be based on the sort of soil weight, the unit weight of the soil, and the pressure it has against the wall if the wind load and lateral loads are pushing up against it. So that would be one of them. And then also just the uplifts in the core, especially in this building. All that wind load was making its way to the core. So we have the core was an elevator shaft and a stairwell. So if you look at an average apartment building, like that's not that big of a space, but we have this huge overturning moment. So for the gravity loads, the piles would be minimal, maybe 1 pile at every corner. But when you actually look at it with the overturning load, we had huge pile groups. We had a 12 or 11 pile cap, 11 piles under one massive pile cap that was probably like, I don't know, I'm trying to remember, 7 feet deep, 7-foot deep pile cap just to be able to transfer all that load, and super wide. So those are definitely the things. The loads are bigger. And when you have uplift, you have to make sure that the piles, when the building rotates and the core rotates, that the piles are secure enough to that core. So you need to make sure, like whether it's drilling dowels in those piles that have anchors or anchor bolts that hook into it so it can develop that tension load, and also make sure that there's enough resistance in the piles to resist that uplift load.
I was just thinking we should finish the timeline of a skyscraper. So from conception to the building being done, if one of you guys could go through that timeline.
Yeah, that's a great question. That's a great question. And I think like a quick answer would be like it varies on different things, because I had 2 different projects and the schedule was significantly different. So there is that project that we're talking about that was built in Canada, and another example that was built in Saudi Arabia. So the one that we recently did in Canada. It starts with a fairly small team. You get the preliminary design going. You make some size some elements and answer key questions. Can the idea work? How tall it can be? What's kind of like the main sizes of all systems, the walls, the columns? What are you going to use to do the typical floor? And that usually doesn't take a lot of time, doesn't take a lot of people. And then that's a critical stage, because the main decision is going to be made, like, is this project good to go? Is it going to be within budget? The owner client satisfied with the answers they got, the number of floors. Of course, the architect is involved. And then once you go into the detailed design, so this obviously takes much longer. Then your team is going to start to get bigger. I mentioned like the example we were talking about, we had like 3 different teams. Like you could say like lateral load resisting team working on the shear walls for lateral load, gravity loads, and the existing foundations and the existing structure that needed to be repaired. I think we had a very tight schedule, and that was part of like the challenge. And we were committed to meet that schedule, and I spent a lot of overtime trying to meet that schedule. But I would say that's the majority of time when you're working like full time trying to meet that schedule would be in the detailed design phase. So we break it down into kind of percentages, like 60% kind of done, maybe 90%. So things are getting closer. And then along the way, a lot of coordination. So I'm actually curious to know what everybody's experience with that. But most consultants, they start working, doing the majority of their work when it gets to the 90% complete. So this is when you start getting all these openings in your shear walls, and mechanical want to change things, and people are catching up with what's happening, and oh my God, this is actually going to be built for real, and we haven't thought much about it. So a lot happens within this 90% mark, and then you issue it for construction. So that's a big milestone, because at least this is how I look at it. Before stamping or sealing something, it needs to be able to be built. So if whatever information on that set of drawings is taken now and built, it should be good to go. But the truth of the matter is, clients, or for whatever reason, I don't want to like blame anyone, things change. Like past the point of issued for construction, there are like some further changes, and then like addendums are issued. And then they get distributed to the whole team to account it, like on top of the issued for construction. Now we have all these addendums. And by the way, go and update your budget and your price and see if you need to go back and do any change in design and issue us a new set of drawings. So it keeps going for a few iterations till kind of the process is satisfied. And then the construction phase. Now I would say I'm not working full time on the project. It's not taking most of my time. But I would get those really urgent questions, because the contractor is on site and they're building the wall, they're building the shear wall, and they come up with a question like, by the way, we ordered a batch of concrete and it didn't meet the target compressive strength. So we have 1 floor or 2 floors of your entire shear walls that are less than what you designed it for. And we need you to give us some instructions. And luckily for that situation, we were using the high strength concrete for the stiffness rather than for strength. So that 1 floor didn't change the entire behavior of the tower. So they were able to continue, and life goes on.
Mustafa, this kept coming up on our Instagram live, and I just figure we just got to answer it here. What was it like working in Dubai?
That's a great question. Wow, like it brings a lot of memories. So here it is. This is my experience, right? Because it was It was pretty much the first thing I ever experienced in the industry. And it was right after school. I'm very grateful I got this opportunity. So I had no reference point to measure anything to it. And it was super exciting and overwhelming at the same time. It's like drinking from the fire hose. I'm not sure what's going on. Is this normal? Is this normal life? Or is this something crazy going on? And the crazy part, the exciting part was all the things that I never got a chance to study at school. Like, oh my God, like we're like 60 floors. What? You're trying to build 60 floors. What? Tall buildings and cool softwares, new softwares for me. Different systems. Like, what is the difference of designing a precast concrete from just cast in place concrete? Like, in school you study the principles, not necessarily the difference between systems. I remember a system was pretty, I think till now it's still used widely, like post-tensioned and pre-stressed concrete. So that was pretty cool to see the whole system of like, designing it and how it's built and stressing the cables and measuring the elongations. So I would say it's a combination of learning a lot of room for growth, building character, getting exposed to stressful situations, but at the same time, tough time balancing life kind of work balance, trying to make it sustainable. So for me, what ended up happening was I gave it my all. I thought, wow, this is crazy what's happening. I want to learn as much as I can, and I want to contribute as much as I can. And it gets tough. Like I have this memory of a meeting. It was with the architect. So the company I was working with, they're a structure design office, and we normally work for like the architect, and they're the lead trade. They're the ones that coordinate with the owners and lead the project. So I was just like, fresh graduate, and I was in this meeting with one of the principals in the architecture office. And we were discussing, like, they were asking us a question, why the beams above the doors and the shear walls have to be that deep. They wanted their doors to be bigger. So, like, me just like, very excited to answer the question from like, after reading a textbook or something like that. Well, we needed it that deep because the seismic reinforcing detail has this kind of diagonal reinforcing, and it needs to fit within a certain depth and things like that. So I guess he didn't like my answer, or he didn't like that I'm basically like, I saying, oh, you can't get the door you need because of some like detail from like a structural detail. So he kind of called me out on like my number of years of experience. He said, like, how many years of experience do you have? And I was like, well, I just graduated last year. And he was like very serious. He said, like, this is a big project. And he kind of left the meeting. So I thought, holy, yeah, this is intense. I'd better know what I'm talking about. So so you'll learn. If it doesn't break you, you'll learn from it, right? So and my boss, he backed me up because he ended up calling my boss. And I wasn't alone. Like it was like, I had other colleagues at the meeting. But yeah, my boss backed me up. And it was situations like this very early on that kind of shaped my career. It kind of very interesting experience. So yeah, if someone is interested, curious how it goes and want to give Dubai a chance, they have the tallest building right now. So the tall building industry is very interesting. And by the way, I didn't get a chance to mention that Saudi Arabia is trying to top that tallest building, and they're planning a Kingdom Tower. That's supposed to be like a kilometer tall, like 1,000 meters. Like,
wow.
This is insane. I was fortunate to attend a meeting, a presentation on the construction of that building, like speaking of like the challenges that comes with super tall buildings. And interesting things come up, like pumping concrete all the way up to build the walls at the top. They needed to do like triple staging. Like they would pump the concrete and then pump it twice and then pump it for the third time to reach the top. It's like things like that.
So you pretty much need an engineer just to figure out the concrete process.
Exactly. Yeah.
I'm looking at some photos. I've seen like the Jeddah Tower. Is that the same?
That's the one. Yes.
Oh, man, I don't know if I'm cut for that.
I'm in.
It's scary, right?
It is. That would just be intense. Like, that would feel so stressful.
Yeah.
And all right. Well, thank you guys very much for joining us. I want to remind everybody to use code SCP25 off. It will be in the show notes, and check out some of the coursework that they have. We've gotten to look at some of it. It's really cool stuff. And talking to these guys, obviously, they know exactly what they're talking about. They know a lot. So thank you guys for joining us.
Thanks for having us.
Thank you so much. This has been fun. Thank you.
Wonderful.